Okay, this problem is a little long. Which of the species have delocalized bonding? Okay, so we actually have to draw out the Lewis structures for each one. So if we start with SO3, we know that the valence electrons for SO3 is going to be sulfur, which has 6, plus the 3 oxygen for 6 each. Okay, gives a total of 24 electrons. Okay, and if we draw this, we know that we have sulfur in the middle, and then we have oxygens around it. Okay, and if we actually work out the Lewis structures for these, we see that we need a double bond for 1 oxygen, and that's going to use up most of our electrons. Okay, make sure you practice drawing these Lewis structures and make sure that you know how to do that, but for time's sake on this video, I'm trying to shorten that a little bit. Okay, and so you're going to have a formal charge of plus 2 on the sulfur, minus 1 for this oxygen, minus 1 for this oxygen. Okay, and since you have this double bond, okay, here, this has resonance, right? This double bond could be here, it could be here as well. Okay, and so those electrons then are delocalized. So SO3 would have delocalized electrons. Alright, so the next one is BF3. And so if we add up the total valence electrons for BF3, we find that we have 24 electrons. Okay, 7 for each of the fluorines, 3 for the boron. Now boron is one of those that can have less than an octet, and so for this we can go ahead and put our 3 fluorines. Okay, and the 24 electrons are going to surround that. So 6 on each fluorine makes 18, plus 3 bonds is 24 electrons. Okay, there are no double bonds there, and so you have no delocalized bonding. Alright, next we have H2CO. Okay, if we add up those valence electrons, we have 2 hydrogens, so that's 2 valence electrons plus 4 from the carbon plus 6 from the oxygen, gives a total of 12. Okay, so we know carbon is our central atom, okay, and we have that bound to an oxygen, and since it tells us H2CO, we know that we have 2 hydrogens bonded as well. Well, we know we can't have any double bonds between the carbon and hydrogens, but we see that the carbon is going to be short on the number of electrons, so we can pretty much add that double bond. Okay, that's going to subtract out 8 electrons, which leaves us 4 electrons left. Okay, and those go on the oxygen. So at this point, we know that there is no resonance for this structure either, because this double bond can't be rotated anywhere else, so those electrons are localized and not delocalized. Alright, so then we have O3, which we solved in a previous video. Okay, and for that we know that we have oxygen bound to oxygen bound to oxygen. We have a double bond. And if you have questions about this Lewis structure, just look back to, I believe it's practice problem 9.1. Okay, and so here, if we draw that Lewis structure for O3, what we see is that we have a double bond between these 2 oxygens. And there's no reason this double bond could not be in between these 2 oxygens as well. So you have resonance, okay? And so that means those electrons are delocalized. Alright, the last one is NH4+, which means that if we look at ammonium ion, okay, total number of valence electrons, nitrogen is 5, plus 4 hydrogens, plus we have to subtract 1 out because of the plus 1 charge, so we have a total of 8 electrons. So if we draw this, we know that each hydrogen can have a maximum of 2 electrons in its valence shell, and so we can draw that, and that's going to use up all 8 electrons. Okay. We also know this has a plus charge, so we have to draw the brackets and a plus charge. And so here we have no resonance as well. Okay, so the only 2 that have delocalized electrons are both O3 and SO3.